Hi, I want to use the kinetic theory definition of the internal energy of a three-dimensional gas to allow us to predict some measurable material properties, namely specific heat capacity. Now, in earlier chapters in our textbook, we talked about specific heat capacity as being something that could be measured in mass. We could also measure it in terms of number of moles. And that context that we're going to use is what we would call molar specific heat capacity, or just molar specific heat. And there are two processes that we're going to focus on because the heat that we would add at those processes is a little bit different. So to investigate heat, we're going to start with the first law of thermodynamics that tells us the change in the internal thermal energy of a gas is equal to the heat that we add to the gas plus any work that we do on the gas. And our first path, we're going to look at starting at some cold temperature, going to some hot temperature, and we're going to add heat but keep the volume constant. Now, if the volume is constant, we're traveling on what we call an isochore, and constant volume means there's no work because the area under a vertical line is zero. So the first law of thermodynamics would just be our change in internal energy is equal to the heat that we add if we're dealing with constant volume. So our change in internal energy is based off of how many molecules we have and the internal energy per molecule based on the equipartition theorem. So if I have n molecules and the average energy per molecule is going to be 3/2 times Boltzmann's constant times the temperature, our change in internal energy would be 3/2 times the number of molecules times Boltzmann's constant times our change in thermodynamic temperature. And since we're going to be talking about moles and molar specific heat, Avogadro's number can factor in here. We divide Avogadro's number into the total number to give us the number of moles. We multiply Boltzmann's constant by Avogadro's number to give us the universal gas constant, R, which is about 8.31 joules per mole per Kelvin of thermodynamic temperature. So the change in internal thermal energy of a three-dimensional gas with no rotation, no vibration, would be 3/2 times the number of moles times the universal gas constant R times delta T. Now, if we add in more degrees of freedom, we add in more total energy. So this is just for the case where, as I said, 3 dimensions for the gas to move in, no vibration, no rotation. Now, applying the first law, well, our change in energy, 3/2 times the number of molecules, or number of moles, times the universal gas constant times delta T, will be the heat that we add. And the formula for adding heat to change temperature went like the number of things, so we're counting in moles. So it would be the number of moles times the molar specific heat capacity, but we're holding the volume constant. So we denote that as C sub V for molar heat capacity at constant volume times our change in temperature. So by playing the match game here, the number of moles cancels, delta T cancels, so this 3D gas should have a constant volume heat capacity of 3/2 times the universal gas constant R. And in a separate video, I'll take a look at some experimental data around room temperature for certain gases and compare it to the expectations and predictions from this kinetic theory model and the equipartition theorem. But if I take 3/2, I multiply by the universal gas constant, that means I'd be expecting 12.5 joules per mole Kelvin for the constant volume heat capacity. Now the other case I want to talk about is if we have an isobar, constant pressure. Now to increase temperature at constant pressure, we would be moving to the right rather than moving up on a graph. So our change in volume would be positive, so the work that we would do on the gas would be minus our pressure, which is a constant, times our change in volume. So the work done on our gas minus the pressure times the change in volume, we have to factor that in, and from the first law, the heat that we add would have a similar structure. The heat we add would be the number of moles. It would be times a molar specific heat, but now it's at constant pressure rather than constant volume, times our change in temperature. Minus the pressure times the change in volume to give us the work that's being done on that gas as it expands. And that would be our change in energy, which would always have to be the number of moles times the constant volume heat capacity times the change in temperature. So in the bottom right hand corner, I've put a few things in boxes. This is a relationship that is true for an ideal gas. The change in internal energy is always going to be the number of moles of gas that we have times whatever the constant volume heat capacity is times the change in temperature. And the first law is also always true too. Those two things are always ways that we could take a look at and evaluate the change in internal thermal energy of a gas. Now, if I take a look at pressure times change in volume, well, using the ideal gas law, my change in volume would be equal to, I would take the number of moles, which is a constant, the universal gas constant, which is a constant, divide by the pressure, which is a constant. So all of those things are constant. The only thing that can change if volume changes is temperature. So our change in volume would be our change in temperature times the number of moles times the universal gas constant divided by the pressure. So if I substitute this in for my change in volume, pressure times pressure cancels out, and my relationship now says the number of moles times the constant volume heat capacity times the change in temperature is the number of moles times the constant pressure heat capacity times our change in temperature minus the number of moles times the universal gas constant times the change in temperature. All three of those terms have the number of moles and the change in temperature, so those cancel out, and I'm left with another general relationship. The constant volume heat capacity is the constant pressure heat capacity minus the universal gas constant, or if you want to frame it positively, the constant pressure heat capacity for an ideal gas should always be the constant volume heat capacity plus the universal gas constant. And there's one more parameter that we need to define because it allows us to talk about the physics of adiabatic processes in pressure-volume space. And that is the ratio of heat capacities that we use the lowercase Greek letter gamma. And gamma is equal to the constant pressure heat capacity divided by the constant volume heat capacity. So that means that gamma is always going to be greater than 1, and the smaller the constant volume heat capacity is, the larger gamma is going to be. Thanks for watching.